Good morning, ladies and gentlemen. Let's talk about waves some more. Transverse waves oscillate perpendicular to the direction of travel. They are going this way. Wave motion is going that way.
You move your hand up and down and the wave goes that way.
And then longitudinal waves oscillate parallel to the direction of travel. So we are compressing and stretching and squeezing, okay, this way. And the wave is also moving that way.
See, there's the rarefaction.
Rarefaction! do they think they know about Scooby-Doo?
I don't know.
Yeah, that was like my childhood. Okay, sound is a longitudinal wave created by a vibrating object, and we saw that yesterday with the door, kind of. Not really.
Yep, the door was vibrating and it made the curtain on the window move.
The vibrating object pushes and pulls on the medium, increasing and decreasing its pressure locally. Locally is important. Okay. The highest frequency on a piano is 4,185.6 hertz.
What does that sound like, Ms. Mo?
Oh, I need my thing. Okay, we've got this online tone generator, and I already put that in there. Ready, set, E.
That's a high and annoying sound. That's the top note on a piano.
That's the top, yeah, that's the top note on piano.
So if the speed of sound is 343 meters per second, how long is that wave?
What is the wavelength of the sound? Okay, so we know that wavelength equals velocity over frequency, and velocity is 343 meters per second, and that frequency was 4,185.6. Now, do you still use hertz here, or do you still
That's cycles per second,
Yeah.
but
okay. Or hertz? Oh, thank you. Okay, so 343 divided by 4,185.6, and we get 0.082.
0.082, that'd be about that long right there.
Dang. Right, that makes sense because it's such a high frequency. The waves are moving. They're really close. The wavelengths are really close together.
Yeah.
The highest oh, I just did that one. I thought it moved. We perceive changes in sound frequency as pitch. How high or low the sound is.
How high or how low the sound is.
So let's go ahead and take a look at our meter stick here. Okay, so.
Oh. Do that again.
Okay.
You could see when it was out very far, it's a higher frequency and then a lower frequency.
And we perceive that change in frequency as that pitch, that sound. And it gets higher pitched the closer it comes in with the higher frequency. Okay, middle C on a piano is 261.6 hertz. And then the A above middle C on a piano, for my piano people here, is 440 hertz. I need my mouse. Oh, mousey. Okay, so the first one was
440. No, we just do 440.
440. Oh, nice.
That's a nice one.
Okay.
All right, well, let's calculate the wavelength. Let's just throw 440 because you've got it over here. Let's just do the same thing.
Okay.
At
So
first-
the wavelength for 440?
Yeah.
343 meters per second divided by
440.
440. CYC. SEC. Okay. 343 divided by 440, and I get 0.78.
0.78. That's
0.78 meters.
0.78. That's 78 centimeters. That's that long. So the higher frequency, shorter wavelength was 0.82 meters long. That's that highest one on the piano. And then middle A above middle C is 0.78.
Now I calculated 0.082 for this.
Yep.
Yeah.
So that's a 8 centimeters.
Yeah. Oh, yes, thank you.
8 centimeters versus 78
The
centimeters.
mental conversion.
That's it.
Okay. Now, if you guys want to get fancy, see if you can calculate the wavelength for a middle C.
Yeah.
Okay, go ahead and do it. Sound waves travel in air as pressure variations.
You have the regular air pressure in the room that's called ambient pressure. There's a sound.
What's the frequency of that? Let's match the pitch.
And what there is there's a speaker that's pushing and pulling on the air at a particular frequency, and when it pushes, it squeezes, and when it pulls, it stretches. And those squeeze and stretch and squeeze and stretch propagate across the room from that bell, not a bell, that sound from the back came all the way to the front, and we heard it.
Into our ear. And then we also have our sine wave, which represents the high and the low pressure.
That's right.
The high and the low pressure.
Yeah, it's a way of visualizing it.
All right, so sound waves carry energy. Ooh, this is a new idea. Sound waves carry energy that can do work on your eardrum.
That's right. They can apply a force and make your eardrum move through a certain displacement.
Yeah, and that's what's happening. Your eardrum, it moves ever so slightly displacement.
Yep.
When I was younger, I burst my eardrum.
Oh yeah.
Yeah, I had a lot of ear. I actually have I had ear surgery on my canals and stuff, and
Yeah.
you know that I've always been pretty sensitive about my ears, and I actually have a hard time hearing things when I get tired. Like it's weird.
Huh.
Anyways,
You don't want to mess around with your ears if you can help it.
Yeah, you know, especially with your eardrum. Loudness is proportional to the amplitude of the sound wave.
What would the amplitude of a longitudinal wave look like?
Okay, so a quiet noise has small lower pressure and higher pressure.
Just a little bit above ambient and a little bit below ambient. That's a quiet sound.
And then a loud noise has a large higher pressure and a lower pressure.
Farther from, it's the displacement from equilibrium.
Mm-hmm.
That's amplitude.
Okay.
And equilibrium would be the normal air pressure.
Going down. Okay. Sound spreads out from its point of origin in spherical wavefronts.
Yeah, if you clap your hands, where does the sound go?
So it goes out in all directions in a spherical bubble.
Okay,
around.
clap your hands again.
Oh, yeah.
Clap your hands again. And again. Okay, so I heard that all over the room. That means a sound was going out, and it starts from its point of origin where you slap your hands, and it spreads out in a big bubble.
Okay. And here's that bubble. Okay. And so what we have here is the origin of the sound, and the way that the sound travels is through locally creating that high and low pressure from the stretching and the pulling of the particles in the air. So right here you can see that they're being pulled, right? And you've got those this dark circle right here is where there's lots of particles being pulled. And then the stretch is right here, and you can see that there's less particles here that are being stretched out.
Yep, and that spreads out. And now this is a two-dimensional representation, but it's actually a three-dimensional bubble that spreads out. It's like blowing bubble gum.
Yeah, and I don't know if they did this on purpose, but they've got these red dots here. And if you were to watch this in live time, like in a video or something, those dots would kind of float back and forth in that spot. They wouldn't move further out. They would just stay in that spot locally.
Yeah, it's not wind blowing. It's not air moving from the source to your ears. It's the pressure disturbance in the sound in the air that travels.
The energy carried by this bubble of sound spreads out as the bubble expands.
Yep.
And we just saw that, right?
Yeah.
Clap our hands, bubble spreads out, expands. This is also a really cool visual. So again, the middle part is where the source, the origin, and the colors represent the pressure.
Yeah, you got zero in the middle is kind of green.
Yeah,
and high pressure is that dark red, and the lowest pressure is dark blue. So the highest pressure is is in the middle.
We've got that dark red and then dark blue. And
And
then
what happens to the red as it spreads out?
and the red as it spreads out and the blue as it spreads out, they're not as dark, right? They're moving in more towards here.
Yeah, the pressure
Right.
variation is less
Yeah.
because that energy is spread over larger and larger surfaces.
Okay. And what does that mean for the loudness that we
That's a
experience?
good question. I think that we get a definition of loudness right here.
Okay. Sound intensity is the sound power passing perpendicularly through a surface divided by the area of that surface. And so what that means is how intense the sound is depends on the amount of power and the amount per area unit that we're
Yeah, an example would be your eardrum. Your eardrum has a certain area.
Yeah.
And the sound intensity depends on the power, the energy per second of the wave that's coming in on your eardrum.
And the area of that eardrum, which is really small.
Yeah.
Okay. So let's go ahead and do an example of this one. What was that equation? Intensity equals
Power over area.
And it says 1.2 times 10 to the negative 4th watts of sound power pass through areas of 4 meters squared and 12 meters squared. What is the sound intensity for each? Okay, so for the first one, the sound intensity is going to be 1.2 times 10 to the negative 4th watts divided by the area, is 4 meters squared for the first one. Okay, and then for the second one, we're going to do the exact same thing. Okay, same amount of power.
Spread over a larger area.
A larger area. Okay. So let's plug this into the calculator. 1.2 times 10 to the negative 4th.
3 times 10 to the negative 5.
Divided by,
4 meters.
oh yeah? Oh yeah.
Well, 12 divided by 4 is 3.
Yeah, so it's 3 times 10 to the negative 5. Maybe one of these days I'll be as good at the mental math as the Boykinator. Okay, watts per meter squared. Yes?
Yeah,
Okay.
that's going to be 12.
And then, that was going to be 12?
This is going to be 1 times
do it?
10 to the...
Should I do it or you got it?
Nah, I ain't got it.
Okay, negative 4 divided by 12, and we get 1 times 10 to the negative 5. Did I put that right? Yeah?
Yep.
Okay, so 1 times 10 to the negative
So the
5.
intensity of the sound would be less over the larger surface.
Yeah, this is oh yeah. Okay, so so that's really important here. So we have a larger surface here, okay, and the sound intensity is less. Okay.
And you have a larger surface, and the sound intensity is more on the top.
Yeah, smaller one. Yeah.
Yep.
Okay. The total power is spread over the surface of a sphere. Okay, so before these ones we were talking about an eardrum, which is just, that's what my eardrum looks like. Okay, but now we're going to talk about the geometry of sound. The total power. Go ahead, Wigan.
This is kind of like blowing bubble gum.
Yeah.
When you chew the gum, you start blowing it, and it's a thick thing of bubble gum, and as it gets bigger and bigger, it stretches, and the same amount of bubble gum is stretched over a larger sphere. So the intensity of the bubble
is going to, well, as it gets bigger.
Yeah, it's going to get skinnier and skin until finally it's so big, it spreads so thin that it pops.
Yeah,
and you get that mess all over you.
So when we talk about the area for a sphere, we have to use our equation for an area of a sphere, which is 4 pi
Area of a
r
sphere. And so
squared.
the sound intensity varies inversely with the square of the radius. As the bubble gets bigger, the intensity gets smaller. And it doesn't just geometrically get smaller, it exponentially gets smaller.
Yeah, so let's go ahead and do a practice problem with that one here. A 40-watt amplifier is turned up all the way. And what will be the sound intensity? Okay, so you said 40 watts.
Yeah.
What will be the sound intensity from 20 meters from the amp?
So that's 4 pi.
20
squared.
Okay. Meters. Just meter. Do I do meters squared here?
No, it's 20 meters squared.
Oh.
So the 20 meters would be inside the squared.
Gotcha. It's like this, people.
There you
Yeah,
go.
because it's like r squared. Okay. Okay, so then let's just go ahead and do that. Okay, I'll have to put the bottom in parentheses.
Yeah.
Divided by 4 pi 20 squared. And I get 0.007, I would call it 80.
0.008 watts per square meter.
And,
So you've got a bubble that has a radius of 20 meters. That's a huge bubble.
yeah, so just to draw this out, you got the amplifier, right? And the sound is going out in all directions, right?
Yeah.
Wagon. And so, you know, as we get further and further away, what is this? We'll call this 20 meters. Okay, that intensity is represented by the area of that sphere.
Yeah.
Right?
And,
'Cause we're talking about this one right here.
and there is that illustration we saw earlier.
Yeah. And the illustration we saw earlier, okay, right here, the further you get out, the less intense that sound is going to be.
Yep.
Okay.
They're going the
Oh,
wrong
I'm the
way.
wrong way. Right there. Okay. All right. So loudness is an opinion.
That's right. There is a way of calculating sound intensity that's called the intensity level. And what it does, it compares the actual intensity of the sound to the lowest, softest sound the human ear can hear. And so it's a ratio, it's a logarithmic ratio between the smallest intensity sound that the human is capable of hearing and the intensity of this particular sound. You've heard decibels.
That's what you do. That's what you used to do
At those rallies, yeah. You have the sound level meter, and it measures in decibels. And I just read the meter. People would always say, Mr. Boykin, you let the juniors win, or you let the seniors win. I don't really care. I just want to get the hell out of the gym.
School spirit.
That's right. Go fight.
Okay,
win.
so what we're gonna do is we're gonna go outside, and we are going to do two situations. Mr. Boykin's gonna be on the sidewalk as I drive the car past, honking the horn.
Yeah.
And the next one, Mr. Boykin will be in the car with me. And as we watch the video,
We'll get to that in a minute.
Okay.
Observe closely what happens. We'll see you outside.
All right, there goes Mr. Boykin, preparing for the thing we're about to do. All right, Mr. Boykin. Dang, reckless driving out here. And let's hop in the car. My chariot awaits. All right, you guys.
You still got it rolling?
Yep, I got it rolling. Oh, this reminds me of my dad's truck when I was little. Okay, thanks. All right. And here we go, ladies and gentlemen.
We're going to turn around. And we're going to hit the horn.
Woo!
What did that sound like?
What was the difference between what you heard outside and what you heard when Miss Moore was in the car with the Boykinator driving? Whoa!
All right, let's go back in the classroom and see what happens.
Okay.
Go!
All right, so now that you have heard the two scenarios, I want you to tell us what happens to the loudness as the car approaches, as the car recedes, and what happens to the pitch as the car approaches and recedes.
Okay, and this is from standing on the side. You're standing from the perspective of the sidewalk What happens to the loudness as it comes and goes? What happens to the pitch as it comes and goes?
And
So that's an assignment. Write this
yes.
stuff down.
This is for homework. And then based on your experience, what do you think caused the change in loudness? And what causes the change in pitch?
Give it a shot, and then we'll talk about it tomorrow. All right.